Assalamu alaikum warahmatullahi wabarakatuh. Our lesson today is on radioactivity. That is the last topic in Form 4, chemistry. So if I make a quick review on book 2, when in structure of an atom and the periodic table, we look at how chemical reactions occurs, and we see that chemical reactions involves the valence electrons. But in this topic, under radioactivity, we are going to see how nuclear reactions occur. And when we talk about the nuclear reactions, you find that it involves the protons and the neutrons. Because in the structure of an atom, we have the nucleus, and the nucleus is made of protons and the neutrons. So when we talk about a nuclear reaction, a nuclear reaction occurs within the nucleus of an atom, and it involves the protons and the electrons. When we talk about chemical reactions involves the valence electrons. So now first we check on stability of radioactive elements. What is the stability? What determines whether an element can undergo radioactivity or not? So we check on stability of isotope. Stability of elements. Stability of elements. So when you talk about the stability of isotopes of elements, there is what determines whether that element can be able to undergo radioactivity or not. And what determines whether an element can undergo radioactivity or not is the ratio of the neutrons to protons in that atom. And when we talk about isotopes is referred to as atoms of the same element with the same atomic number but different mass number. Isotopes are referred to as atoms of the same element with same atomic number but different mass number. Therefore, you will find that some of the isotopes have relatively more neutrons than the others. So the percentage abundance of those isotopes are more than the other. For example, if you look at chlorine, we have chlorine 35 and we have chlorine 37, 17. This one has a percentage abundance of 75%, and this one has a percentage abundance of 25%. Therefore, what happens is that the number of neutrons that they are having differs. That's what's going to cause their differences in mass number. And now to determine the stability, there is that range. Most of the isotopes, most of the elements, you will find that the ratio of neutrons to protons is in the ratio of 1:1. So we say those elements are stable and they cannot undergo radioactivity. So we talk about the stability of elements is determined by the ratio of N:P, whereby you are going to find that most of them have the ratio of 1:1. For example, if you look at calcium, this is number 20, 40, and this one here is 20. This one there is 20. So, calcium atom has 20 protons with 20 neutrons, because a nuclide is defined by the neutrons and the protons that it is containing. Therefore, we are going to find that the ratio of neutrons to protons is going to be 20/20, which is going to be 1:1. So we say this element is stable. So as the number of nucleus continues to increase, which means the ratio also continues to widen, and you'll find that the range of stability is within up to the range of 1.6. So we talk about stability of isotopes is up to the range 1.6:1. So if you find that the ratio of neutrons to protons is within the range of 1.6:1, then we say that that element is still stable. It is still stable. But as it progresses, it becomes bigger than this, then that shows that that element is unstable, and we say that it is a radioactive element. So, unstable elements, we say that unstable elements that can undergo radioactivity, are said to be radioactive elements. We say that those elements are radioactive. They are radioactive. So they will undergo radioactivity, and during the process of radioactivity, they will be resulting in emission of particles and giving nuclides with different composition. So this results in to talk about as radioactivity. And there is also emission of energy. Now, what is radioactivity? Radioactivity. So we say that radioactivity, this is the So we say radioactivity is the spontaneous disintegration of unstable nuclides to form new nuclides with different composition, with an emission of particles and energy. So we say this is the splitting of unstable nuclides. Unstable nuclides to give new nuclides with different composition, with an emission of particles. and energy. So we say that radioactivity is the splitting of unstable nuclides to give new nuclides with different composition with an emission of particles and energy. So that's what we mean by radioactivity. Then we have radioactive isotopes. So from the word isotopes, we have already said that isotopes are atoms of the same element with same atomic number but different mass number. So isotopes, unstable isotopes, are said to be radioactive isotopes. Radioactive isotopes. So we have radioactive isotopes. Talk of radioactive isotopes. So we say these are unstable isotopes of an element and can undergo radioactivity. So we talk about radioactive isotopes. So we say these are unstable isotopes of an element and can undergo radioactivity. Then we have radioactive decay. Radioactive decay. Radioactive decay. What do we mean by the radioactive decay? So we say that radioactive decay is the spontaneous disintegration of a radioactive element with an emission of nuclides with the different composition. Also, we have the particles being emitted and energy also being produced during radioactive decay. So we say that radioactive decay is the spontaneous disintegration of a radioactive element with an emission of particles and energy. So we say radioactive decay is the spontaneous disintegration of a radioactive element with an emission of particles and energy. So that is what we talk about as radioactive decay. Radioactive decay. Now, we have looked at nuclear reaction, and we have seen that a nuclear reaction is involving the protons and the neutrons, while a chemical reaction is involving the valence electrons. So, from the two, we can be able to give some of the differences between a nuclear reaction and a chemical reaction. Let's have a look at some few differences between a chemical reaction and a nuclear reaction. Chemical reaction and a nuclear reaction. So we make it in table form. So we have here nuclear reaction. Here we have chemical reaction. We have chemical reaction. So one of the differences between a chemical reaction and a nuclear reaction. One, we say that a nuclear reaction involves the nucleus, where we have the protons and neutrons. So involves protons and neutrons within the nucleus, while this one involves valence electrons. It involves the valence electron. That's the first difference between a nuclear reaction and a chemical reaction. The second is in terms of energy being released or absorbed. In a nuclear reaction, there is no absorption of energy. Always there is release of energy. And when we talk of release of energy, large amount of energy is being given out. And that is why we use nuclear reactions in production of electricity. And in a chemical reaction, energy will either be absorbed or released. And only small amount of energy will either be absorbed or released. So we say here, large amount of energy is released. Large amount of energy is released. But when we come to a chemical reaction, so we talk about small amount of energy, small amount of energy is either absorbed or released. Small amount of energy is either absorbed or released. And when we talk about the absorption of energy or release of energy, now that results into either an exothermic reaction, that is the release of energy into the environment, and endothermic reaction, which involves absorption of energy from the environment. So this here, we have two types of reaction where we have exothermic and endothermic reaction. But in a nuclear reaction, energy is always released. There is no absorption of energy. And the third difference between the two, the third difference between these two here is in terms of factors that affects this reaction. Nuclear reaction cannot be affected by environmental changes. Is not affected by environmental. Is not affected by environmental changes. While chemical reaction, this one here is affected by environmental changes. Is affected by environmental changes, e.g., we talk of temperature. So when we talk about a nuclear reaction, this reaction is occurring within the nucleus of an atom. Therefore, things like temperature, we talk about pressure, we talk about catalysts. Those one cannot be able to affect a nuclear reaction. But when it comes to a chemical reaction, we have factors affecting the rate of a reaction. Temperature is one of a factor. We have pressure being another factor. We have concentration. So all these factors are affecting a chemical reaction. But if it's a nuclear reaction, you find that these environmental changes does not affect a nuclear reaction. Then from there, we move to types of radioactivity. Types of radioactivity. Types of radioactivity. We have got two types of radioactivity. One, natural radioactivity, and another one is artificial radioactivity. So the first one is natural radioactivity. And the second one is artificial radioactivity. So when we talk about natural, from nature, from the nature, so this one occurs naturally. And the difference between natural radioactivity and artificial radioactivity, you will find that in natural radioactivity, it is the disintegration of unstable nuclides. So which means unstable nuclides or radioactive elements are undergoing radioactivity. They undergo disintegration, resulting into emission of different nuclides with different composition, with an emission of particles and energy. But when we talk about artificial, this one is initiated. So it occurs on unstable nuclides. So here it is the stable nuclides which are undergoing radioactivity. And how does it happen when we have a stable nuclide undergoing radioactivity? So this stable nuclide is going to be bombarded by a fast moving neutron so that it can be able to undergo radioactivity. So here, natural radioactivity, we talk about unstable nuclides. Unstable nuclides undergoing radioactivity. Or we talk about radioactive elements undergoing radioactivity. But when we talk about artificial, it is stable nuclides undergoing radioactivity, when bombarded or when hit by a fast moving neutron. So that is what we are going to have as the two types of radioactivity. So the first one we have said is the natural radioactivity, and the second one is artificial radioactivity. Now, let's have a look at the types of particles that are being emitted during radioactivity. Types of particles emitted during radioactivity. Under the types of particles emitted during radioactivity, they are three. One, we have alpha particle. Two, we have beta particle. Three, we have gamma rays. So we have types of particles emitted during radioactivity. So one, we have already said that we have the alpha particle. We have alpha particle. Two, we have the beta particle. Alafu three, we have the gamma rays. So alpha particle is represented by this or that one there. And beta particle is represented by that. And we have the gamma rays which are represented by that. So that is the representation of an alpha particle, a beta particle, and the gamma rays. Now let's have a look at characteristics of these particles. So we have characteristics of the particles. Characteristics of the particles. So when we talk about the characteristics of the particles, we have the alpha particle. Alpha particle is positively charged, and during its emission there is emission of an helium. So we say alpha particle is positively charged. It has a charge, is positively, alpha particle is positively charged. It is positively charged. That is 2 positive with an emission of helium. With an emission of helium, which is He, that is 4, 2 positive. So it has a charge of a positive charge. Then we have the beta particle. The beta particle, Beta particles are negatively charged. So this one here is negatively charged and is represented as an electron of 0 and -1. That's the representation of a beta particle. So this electron here does not originate from the valence electron, but it originates from the nucleus. When a neutron is emitted and is being converted to proton, that is what results into this electron here. So we say that the electron being given out here represents electron from the nucleus and not from the valence electrons. And it is as a result of when a neutron particle is being converted to a proton. So we are going to have a neutron 1 being converted to a proton of 1, then we have electron of 0, -1 plus an electron of 0, -1. 0, -1. So this one here is 0. Here we have 1. So we have a neutron here being converted into a proton, then we get an electron. This negative charge here does not represent the atomic number, but the negative charge represents the charge of the beta particle. So it has the negative, so we say, so the negative charge, -1, represents the charge on the beta particle. It represents the charge on the beta particle. So this is what we're going to have as a beta particle. Then we have an alpha particle. The gamma rays, not alpha. We have the gamma. We have the gamma rays. The gamma rays. This is 1, this is 2, and this is 3. The gamma rays have no charge. They have no charge. And during their emission, during the emission of the particles, so gamma rays are being emitted together with the beta and the alpha particles. So we say have no charge and are emitted together with beta and alpha particles. So this gives us some of the characteristics of the particles that are being emitted. That is the alpha particle, the beta particle, and the gamma rays. So let's have a look at the properties of these particles. What are some of the properties of these particles? So when you talk about the properties of the particles, properties of the particles What are some of the properties of the particles? One, we check the properties of the particles in terms of the penetration power. So the first one is penetration power. We talk of the penetration power. When we talk of the penetration power, we are trying to check how far can the alpha particle, beta particle, or the gamma rays penetrate certain objects? The first one, we have the alpha particle, which has got the lowest penetration power, and that one can be stopped by a piece of paper. If we can know that a certain radioactive element is undergoing decay by emitting an alpha particle, then we can shield whatever that's around, or we can cover it using a piece of paper. That is to prevent the penetration of these radiations within or to the environment, or causing dangers to the living organisms around. That is the alpha particle. So we have said that alpha particle has the lowest penetration power and is stopped by a piece of paper. Then we have the second is the beta particle, which has the second penetration power. Beta particle can be stopped by an aluminum foil. Aluminum foil. I hope you understand what aluminum foil is. The one that maybe you also find the chefs using if you want to keep your food hot. So after cooking the food, you cover it using an aluminum foil. Or even apart from that, we have the packet of the cigarettes. Inside there's that thing which is very shiny. So we have that one as an aluminum foil. So an aluminum foil can be used to stop the radiations, the particle radiations. We talk about the particles, or the beta particles from penetration. Then we have the gamma rays, which have got the highest penetration power. These ones can only be stopped by lead blocks. Lead blocks. So which means thick blocks of lead are the ones which can be used to stop the gamma rays. So under the penetration power, so we say that alpha particles, have the lowest penetration and can be stopped by piece of paper followed by the beta particles, which are stopped by aluminum foil, and lastly gamma rays with the highest penetration power. And can be stopped by lead blocks. So if we have a radioactive element here, so that is radioactive element. Then we have piece of paper. We have here an aluminum foil. And we have the lead blocks. So this one is piece of paper. This is aluminum foil. While this one is lead block. So we have that one that will be stopped here, and we have another one that will be stopped here, and we have the last one that will penetrate up to that. So we have the one that is going to be stopped here represents the alpha particle, then this one represents the beta particle, and this one here represents the gamma rays. So this is the representation. This one here is a radioactive element. As it undergoes radioactivity, we are making an assumption that it releases all the particles at the same time. It releases an alpha particle, a beta particle, and the gamma rays. Therefore, we are going to find that if we arrange piece of paper, aluminum foil, and the lead block, alpha particle is going to be stopped by a piece of paper, while the gamma and the beta particles are going to penetrate the piece of paper. But when we reach on aluminum foil, it's only going to stop, that is on the beta particle. But the gamma rays will still penetrate the aluminum foil and will only be stopped by the lead blocks. So this gives us some of the property of the radiations. Then the second one is deflection by an electric field. We check on deflection by an electric field. Deflection by an electric field as the second property of the radiation. Deflection by an electric field. So we have deflection by an electric field. The second one is deflection. Deflection by an electric field. So when we talk about the deflection of an electric field, we are trying to see what is going to happen on these radiations. Which side of the charge will they attracted? From the law of magnetism, we know that like poles repel while unlike poles attract. Therefore, you are going to find that an alpha particle which is positively charged is going to be attracted towards the negative charge of an electric field, while a beta particle which is negatively charged is going to be deflected towards the positive charge, positive side of an electric field. And we have the gamma rays which have got no charge. That one will not be deflected on either side of an electric field. Therefore, it will travel straight. This one here travels straight. So under the deflection by an electric field, we say that alpha particle being positively charged, is deflected towards the negative side, while alpha, not alpha but the beta particle, which is negatively charged, is deflected towards the positive of an electric field. So that is what we're going to have as the deflection of that. Therefore, if we have a radioactive element here again, this one here represents a radioactive element. We have that as the radioactive element. We have the positive side and we have the negative side of an electric field. So there is that the radiation that will be deflected towards this, and there is that one that's going to be deflected towards this, and we have that one that moves straight. So we find that the one that is going to be deflected towards the negative side of the field, the positive side of the field, is going to be a beta particle. Since it is negatively charged, gets deflected towards the positive, and we have an alpha particle which is negatively charged, gets positively charged, gets deflected towards this. And the one which travels straight represents the gamma rays. And we have said that an alpha particle can be represented that way or this way. So this is the representation of an alpha particle. And the last properties, the last one, which is on the third property, is ionization. Ionization power. Ionization power. So when we talk about ionization, how are they able to form ions when traveling in air? So we have an alpha particle being the heaviest and slowest in terms of movement. It will have more time to ionize or to form ions in the air when targeting the object, followed by the beta particle, and lastly we have gamma rays. So we say that alpha particle being the heaviest and travels slowly, has the lowest penetration, has the, not lowest, but has the highest ionization, has the highest ionization power, followed by the beta particles, and lastly gamma rays. So that is what we're going to have in terms of ionization, how they form ions as they are traveling in the air. So gamma rays, being the lightest and travels very fast in the air, so they will take less time to ionize since the speed is very high. And alpha particle, which is the heaviest and travels very slowly, therefore will ionize, will give more ions as it travels slowly. And that marks the first lesson of radioactivity. The second lesson is going to start from radioactive decay and half-life. So we are going to start on radioactive decay and half-life as our second lesson on radioactivity. Thank you.